Hi, we're Group 26, Team Maverick. I'm Evan Marshall.
I'm Jimmy Oates.
I'm Jack Hinger.
Our project was to develop a micro-air vehicle, or MAV. An MAV is a small autonomous or semi-autonomous aerial vehicle. Our project was to develop a control and stabilization system for a commercial hobby helicopter and lower the entry barrier of skill for potential pilots.
A MAV is useful in applications where a quickly deployable, stable, easy-to-fly aerial vehicle will be desired. The military has been expanding into this field for a while, but we believe that the private sector would be interested in this as well. Possible applications are geological surveying, wildlife surveying, bridge inspections, and police surveillance.
The technology that went into this MAV began with off-the-shelf chassis for a helicopter. Ideally, this helicopter and constituent components would provide a out-of-the-box, airworthy platform for us to control. On the control side, we used a microcontroller connected to a Wi-Fi module to facilitate communication with the controlling laptop, an IMU to determine the orientation of the vehicle, and GPS to determine the location of the vehicle. With these inputs, the microcontroller could then output controls to the servos and motors of the helicopter to stabilize its flight.
The power and blade control system consists of level shifting, PWM signals, servo layout, motor control, and power rails. The master control code coordinates between the main control loop and all of the peripheral control loops. This includes the blade control, the wireless communication, as well as the sensor servicing. It also handles real-time counter to track and run certain things at specific times, as well as setting up the timers for the PWM signals. Motion control code consists of taking user input and sensor input into the PID loops, mixing them together, getting an updated value that goes to the PWM control code, which then updates the actual PWM values that go out to the servos to control the helicopter. The PID control loop is a classic control system that stands for proportional, integral, and derivative. The proportional term is the measured error between the desired location, which is the user input, and the measured location, which is the theoretical actual location of the system that's measured through sensors. The integral term is accounting for steady state error, which is the discrepancy between the sensors and the user input, and accumulates the error over time to account for this error. The derivative term is used for dampening of overshoot. It measures the rate of change of error over time and prevents overshoot and oscillations. There are three main power rails to our system. There is an 11.1 volt rail that is used for the motor controller and controlling the motor, and a 5 volt rail that comes out of the motor controller that goes to the MCU and a linear regulator. The linear regulator drops the 5 volt rail down to 3.3 that is required for some of our other components.
The MCU block is a microcontroller unit. In our case, we chose the Atmel AVR UC3A3256 microcontroller. The MCU's task is essentially to communicate with all the peripherals on board the helicopter in order to get and send data. And it also does all the processing upon the data that controls the flight. The IMU block is composed of an accelerometer and gyroscope connected to the MCU or an SPI bus. This bus allows the devices to be configured and data retrieved from them. The accelerometer is the sensor that measures linear acceleration on 3 orthogonal axes. The gyroscope also measures data on 3 orthogonal axes, but in this case, measures rotational velocity. The data from these two sensors is used by the IMU processing algorithms to determine the orientation of the device. The IMU processing block takes in raw data from the accelerometer and gyroscope and runs it through Sebastian Madwick's IMU algorithm. This algorithm takes in the signals, filters out noise, and combines the linear accelerations and rotational velocities from the sensors in order to come up with an overall better guesstimate of the orientation of the craft, much better than can be achieved through more rudimentary techniques.
The chassis. When we started the project, we didn't know what kind of chassis we wanted, whether it would be a helicopter, an airplane, or some other more obscure airframe. We decided on the helicopter due to its availability, affordability, and already being a proven design. Our chassis is a medium-sized hobby helicopter. This provides a balance of power, maneuverability, and portability. There are three alternatives considered for the wireless hardware. A hobby RC transmitter, which is relatively expensive, difficult to interface with, and does not offer any options for sending telemetry back. The Zigbee protocol has a longer range than either of the other two options, but requires a module at either end and offers a relatively low data rate. Wi-Fi needs only one module, as Wi-Fi is present in many consumer electronic devices already owned, and has a relatively high data rate.
In choosing the MCU, we had a great deal of options, ranging from the simplicity of an X-Mega up to the complexity of a BeagleBoard. We ended up going for the middle ground with an Atmel AVR QC3A3256. This processor had plenty of memory and power for our application, as well as a very nice competitively priced development board. In constructing the high-level program flow on our MCU, we initially tried using FreeRTOS to mediate between the various resources and tasks that needed to be run. However, FreeRTOS turned out to be a lot more complex than we needed, so we ended up using the real-time counter on the microcontroller to arbitrate when processes would run.
Here is the entire Maverick setup. We have the operator station and controller, and the MAV itself. Now before we even connect, let's take a look at the control algorithm. Now if we look at the swash plate here, and we tilt the helicopter, you can see that the swash plate moves opposite the orientation of the helicopter to try and compensate for that tilt. And that's true for the roll as well. And if we look at the tail, you can see if I turn it, it is perturbing the tail. Now let's go ahead and kick it up a notch. We will start the control system on the computer, and we have our controller here. We can give it a little bit of collective, so that will cause the helicopter to gain elevation, lose elevation. There's some left roll, right roll, forward pitch and rear pitch. And then also on the tail we have torque and anti-torque, and that's all being controlled by the controller. So this is a test of one of our safety features. You'll actually get to see the helicopter spin up now, and then I'm going to turn off or disconnect the wireless connection, and within a second of disconnect it will power down the throttle. So we're already connected, so I can give it power. So this is actually the minimum throttle. It's not even anywhere close to taking off. Now I can disconnect, and it's powered down.
For next year's seniors, if Don tells you your project is going to be hard, listen to him.
Push yourselves. If it seems like what you're doing is easy, you're probably going to encounter something much harder later on. So go ahead and get ahead now. That way you have more time later to work on the really tough things.
When you're buying components, you usually get what you pay for. So if something looks really cheap and too good to be true, it most likely is.
If your project uses any sort of embedded design or microcontroller, take Core 73 if you get a chance. I don't think our project would have been as far as it had if all of us hadn't had the class. Yeah!